Now we're going to look at more about complex multiplication from the algebra side, but really with the intent of trying to understand the geometry that's encoded by it, because we've seen that all the other operations, addition and multiplication by a real number, do encode some simple geometry. And this is really the heart of one of the big keys to the whole story. What does it mean geometrically to multiply a complex number, let's say some random complex number z, by I? If you take z goes to iz, I want to think of that as a transformation of the complex plane. And so we want to know what that does. Well, if you don't already have an idea of it, then just put in some z's and see what happens. So, good time to pause. Well, 1 goes over to I, of course. I becomes minus 1. That's, of course, the whole point. I squared is minus 1. Minus 1 goes to minus I, which is going to be down here. And then minus I times I, nice little exercise, it's back to 1. Okay, well, let's see. What about if you took like 1, well, let's see, like 2 plus 2I. What does that do? Okay, you multiply that by I, you're going to get 2I plus 2I squared, or 2I minus 2, or put it in standard form, minus 2 plus 2I. That's over here. Go left 2 and up 2. Okay, notice what's happened. I've rotated counterclockwise by 90 degrees. And in general, I times a plus bi is going to be, the I squared is going to give you minus b plus ai. Okay, and what's that going to do? It's going to take something that if you have like a triangle with this being a and this being b, it's going to produce another triangle with this vertical being the new horizontal but negative, and this horizontal switching to vertical. And so there's minus b and a, and that's going to be a 90-degree rotation. And that's super, super crucial, that somehow multiplying by a complex number has to do with rotation. Notice one thing is that these points are getting neither further or closer to the further from or closer to the origin. It's just a pure rotation. In this case, it's a 90-degree rotation. Alrighty, so part B asks, what about multiplying by minus I? And I'll leave that for you to think about. Okay. Part C gets you a little more complicated multiplication geometry. The question is, what if you take z and you multiply it by 1 plus I, the quantity 1 plus I? Okay, what's the geometry here? Well, so this one I'll do. And the hint is, I'm specifically asking what happens to the magnitude and direction of these guys, thought of as vectors or as points on the plane, but you want to think of them as arrows. Okay, so the 1 vector, or complex number, turns into 1 plus I, which is like this. Notice it's longer. Okay, but it is rotated. 1 plus I, hey, might as well do that one. 1 plus I squared, that's an interesting one. Why don't you do that? Pause and do that yourself. If that actually turns out to be 2I. The real parts cancel out. Huh, that's again longer, but again rotated by the same amount, 45 degrees. What if we took, well, if we took minus 1, it's easy to see that goes to minus 1 minus I. Okay, notice it's longer by the same amount, the same factor. In fact, it might make sense to look at the lengths of these vectors. This was 1, this is root 2, because it's just a 45, 45, 90. This guy, it's 2I, so the length of that thing is 2, if we just forget the fact that it's going the I direction. So 1, root 2, 2, that's interesting. 1, and then this is a root 2, because this is just minus 1 minus I. That's another 1, 1, root 2 triangle. Okay, I'll let you do another few if you're not convinced already, but it looks like what it does is it rotates everything by 45 degrees counterclockwise and scales by root 2. Interesting. Okay, and then D, I'm not going to do it for you, but let's say, let's take multiply by 3 minus 4I, and as you do this, you can probably, if you can't figure out why I chose the numbers 3 and 4, then you're probably not doing the problem correctly. So try that out. Okay, so rotates and scales. That's very interesting. So let's make that more systematic. There's a great way to make that more systematic. Let's see if I can try to do this. No, it really does bleed through. That's too bad. Well, not bleed through, but it shows through. There's one. Here's where I'm going to give some big hints, because it's just, there's definitely ways that are a little bit more discovery based and less slick, but I just love how slick this works out if you do it the right way. So this is number 5. We've already gotten a hint. I've already given you a hint that it's really useful to take. So, whoops, just kidding. I'm getting confused here. Okay. If z, I was trying to write two things at once. If z is a plus bi, then what we define is the magnitude, although often in the complex plane it's called the modulus. But it's really the magnitude of the vector, a plus bi. Okay, because you're just going a over the right and b up this way, and there's z, and the magnitude of this guy, that's just Pythagoras. That's just the magnitude. Okay, and super useful is one operation that we haven't introduced yet. If you're at all familiar with complex numbers, you might be wondering, why hasn't he talked about this yet? Here's z, which is a plus bi, and what's called the complex conjugate is just a minus bi. It just reflects, and it's just a z bar. Complex conjugate. It's usually just called the conjugate, but conjugates show up a lot. Various different kinds of conjugates show up a lot in mathematics. Specifically, it's the complex conjugate. It's reflecting across the real axis. Okay. Turns out that excuse me. Turns out that the relationship of this with this is very tight, and together they help us do a lot of good stuff relating the algebra and the geometry. So, now do I have yes, I do have a fresh sheet. Okay, so here's some things in number 5. I don't know if I'm actually even going to do these. The claim is that the magnitude of a complex number is always greater than or equal to 0. It's a real number, first of all. It's always greater than or equal to 0. And if it's equal to 0, the only way that that's true is if the complex number itself is equal to 0. So it's a genuine measure of size, is what that says. The technical language is that it's positive definite. Okay. Why are we using this bar notation? I thought that meant something else. I thought that meant absolute value of a real number. Well, we want to show that the absolute value of a real number considered as a complex number, you just take r plus 0i, that's really just the ordinary absolute value. So this is r squared plus 0 squared square root. We want to know if it's equal to that. That's pretty easy. Okay, so that means the notation's consistent. So I'm going through these pretty quickly because they're really things that I think are much better if you do them. And let's see, let me look at my other screen here. Okay, I already mentioned that the conjugate reflects the complex number across the real axis. Okay, and I'll just put in, when is z bar equal to z? Okay, and when is z bar equal to minus z? Do these detect something interesting and special about a complex number? Of course, the answer is yes. And whenever you introduce a new operation, you should see if it plays well with other operations. So first, we'll see if it plays well with addition. That's a really good thing to check, and really easy. That the complex conjugate of a sum is the sum of the conjugates. Okay, so very basic stuff. And it brings a reflection into the story. We got a hint that rotations are important, and they're going to be absolutely crucial. But whenever you do consider rotations, you probably want to think about what reflections do, because they're a very similar kind of geometric operation. Preserves lengths and angles, things like that. But flips everything and makes things rotate the other way, which can be quite significant. Okay, so number 6, let's say, I think this is probably going to be the last one for this video, okay, because we're going to be able to go back to the calculus after this one. Maybe that'll be a natural break. Okay, so here's some other good ones to show. We want to figure out how these operations relate to multiplication, because that was the really interesting thing. Okay, so A, there's various things to show. ZZ bar is supposedly the magnitude squared. This is super. Magnitude, obvious geometric import. The bar, reflection, interesting geometric, maybe not as compelling as this guy, and multiplication. This relates all three of those very, very tightly. Very, very tightly. Okay. And then here's the one that we'd really like to be true. The bar of a product is just the product of the bars. Okay. Just direct, these are direct computations. Just write out a plus bi, z equals, and w equals c plus di, and check both sides. Okay. But they are really nice because now they start to really pay off dividends. I claim that just from the previous two parts, we can see how the magnitude and multiplication relate to each other in a very slick way. Okay, so that's for you to check that the product of the magnitudes is the magnitude of the product. And that actually really answers our question about the geometry of multiplication. Here's why. Okay, let's look at a special case. If the magnitude of w is equal to 1, then it's pretty obvious from the previous thing, then the magnitude of wz will just be the magnitude of z. Now, here's why this is so crucial. Let's think about the perspective. Let's think about w as fixed and defining a transformation. Okay? And then z is going to be the input of that. Okay? So this is really like, you could think of this as f of z is wz. And I'm asking, what does that function do? What does multiplication by some fixed complex number do? And we're going to look at the special case where the magnitude of that guy is 1. So this would be called a unit complex number. Really short for unit magnitude complex number. Sometimes that can be a little ambiguous. Okay. It doesn't mean it's literally 1. It means its magnitude is 1. Okay, well, what does this say? It says that wherever z goes, it's somewhere with exactly the same length. Okay. So it's going to be some transformation, and we know it's a transformation that respects addition because of the distributive law. So like w on z1 plus z2 equals wz1 plus wz2. Okay, it's some transformation that respects addition and scaling and doesn't change lengths. Well, I'm not going to prove this, but there's only a couple things it could be. It could be a rotation. It could be something where everybody gets rotated by the same angle. So that guy gets rotated that much, that guy gets rotated by the same amount, this little guy gets rotated by the same amount, and the input and output all have the same length. Okay, so it could be a rotation. Now, we got to get rid of one possibility, though. It could be a reflection. That's definitely a nice transformation that respects addition and parallelograms, things like that, and lengths. And we'll get rid of that in just a second. Okay, but we also want to figure out, well, wait a minute. That was just for a unit complex number. Maybe multiplying by a non-unit complex number is much more complicated. Let me see if I can save some paper here. That looks kind of weird. I feel like I'm wasting paper, though. Okay, ignore the little dots at the bottom. Okay, so that's what problem 5 is about. V. Okay, it's pretty obvious what multiplying by 0 would be, so let's not worry about that. Okay, then, well, I'm not going to assume it's a unit complex number, but there's a very easy way to relate it to a unit complex number. What can you tell me, oops, that says W, about taking W and dividing it by its magnitude? Okay, well, the claim is, okay, so that's another one you should check. Okay, that's really supposed to be a W. That's a unit complex number. So this is just a very basic thing with vectors. I've begun to understand, and I still have some questions about what happens when I multiply by a W like this. Well, what if W actually was like this? I can always take an arrow and scale it down, and the way you do that is you divide by its magnitude. This is just exactly something that if you've done anything a significant amount with vectors, then this is familiar. Okay, so, okay, so that's going to let us figure out what happens for a complex number that's not a unit. Let me start trying to use up this paper better. Okay, so now, so there's one thing that we really need to do. let's look. We kind of already know the answer to this. We want to look at what happens. Is it a rotation? Sorry for being tongue-tied there. Thinking something else. Is it a rotation or a reflection? And you just have to put in a couple inputs. So here's some w, a plus bi. Let's say it's here. Okay. Well, I'm just going to compare. Let's look at w1 and wi. Okay, it's another good place to pause it. Draw a picture of w times 1 and w times I, and 1 and I. Okay, so let me put in blue. Here's 1 and here's I. Okay, and notice that their relationship is that if I go from one to the other, from 1 to I, it's a counterclockwise rotation. Okay, now we already noticed what happens when we multiply something by I. Okay, it's a rotation. But now we've got a little bit of a different perspective. I'm not thinking of it I rotating W. I'm thinking of W being the thing that's rotating I. But you know what? It doesn't really matter. It's commutative. It's a commutative multiplication. And so here's WI. Okay. And now what do we notice? Okay. The 1I pair going from this one to this one is a counterclockwise rotation. And that's the same thing going from W1 to WI. So multiplying by W could scale these blue vectors to make the green vectors. They can rotate, but it's not flipping. It's not changing the orientation of the plane. If I was reflecting, I would take counterclockwise rotation, and that would become a clockwise rotation. Okay. So for example, something that does reflect is z bar. Z goes to z bar, right? Here, if the inputs are 1 and I, counterclockwise rotation. Okay, then I'll write the outputs on a different one just so it's not confusing. Well, 1 bar is 1, and I bar is minus I, and now that rotation direction has been reversed. Okay, so if we were at all worried about whether we were being too cavalier and thinking this was a rotation and not a reflection, that should answer the question. Okay, so, and we're almost done with this one. This actually turned out to be longer than I expected. That's okay. A lot of stuff. It's important stuff. Okay. So now we can finally answer the question. For any w not equal to 0, what does the transformation z goes to wz do? Okay. Well, first, let's multiply, and this is the answer to part C. And so another good place to pause it. Think about how this A5, the V in 5, Roman 5 in A is going to be really helpful here. What we can do is we can first, I keep wanting to put a Z there. First, just multiply by the unit vector version, the unit complex number version of W. And then put back in the real version, the real number magnitude of W. I keep writing it Z. Okay. This guy's multiplication by unit complex number. We just figured out it was definitely not a reflection. It is a rotation. Because that's the only thing that's a nice transformation of the plane that preserves orientation and length. And then this guy is just a scaling. We already figured that out a while ago. Because that's a real number. And so it's really crucial. What we're using is a really important thing is, again, that any complex number can be factored into a real number, the scaling part, magnitude of W, times that unit complex number. You tend to use that a lot. Okay, so this is a rotation and scaling, and that's what multiplication by complex number achieves. And we know how to flip things using across the x-axis anyway, using the complex conjugate, and we also know how to shift stuff by adding. So pretty much all the interesting geometric operations you want to do are implemented exactly in the algebra of complex numbers, and that is one of the huge, huge links here. So remember there are 3 perspectives here: algebra, geometry, and analysis, or calculus. And we've now got a very tight link between the algebra and the geometry part. And then in the next video, we'll go back to link it to the calculus, because after all, that is going to be how we solve our motivating problem.